Welcome to the Deep Dive. Today, we're tackling a really fundamental question, something that changes how we think about electricity moving around.
Yeah, we normally picture electricity flowing through a wire, right? Simple enough.
But what happens when the frequency gets incredibly high? We're
Yeah.
talking gigahertz, microwave territory.
Uh-huh.
Suddenly, those wires, well, they don't cooperate anymore.
Exactly. They start fighting back, in a way. At those frequencies, your standard wires, even traces on a circuit board, they become really, really good antennas.
I mean, they just radiate energy away,
What?
lost into space.
Precisely. The fields just spill out. It's inefficient. So, we need a different solution. And that's what we're deep diving into today, waveguides.
Waveguides, okay.
These are often hollow metal pipes or similar structures, and their job isn't really to carry current in the traditional sense, but to very strictly guide the electromagnetic fields themselves, contain them.
So our mission today is sort of tracing how we get from a normal cable to this, well, pretty radical idea of a hollow pipe guiding energy.
That's the plan. We're leaving the world of lump circuits behind, where the physical size doesn't really matter for basic calculations.
Right, like for standard 50 or 60 hertz power.
Yeah. Here, the frequencies are so high, the wavelengths are so short that the physical dimensions are everything. We need precise control, precise containment.
We're talking about fields moving too fast for simple wires.
It's about wave propagation, not just current flow. We have to manage the signal's integrity, and that means focusing on the space between conductors, or even inside a hollow conductor.
Okay, so where do we start? Let's begin with something familiar, right? The most basic kind of guided structure.
Absolutely. Let's talk about the transmission line. And the classic example, the one you probably have connected to your TV or internet modem, is the coaxial cable.
That shielded cable, inner wire, outer mesh.
That's the one. It's a great starting point conceptually. We don't just use Ohm's law here. Instead, we imagine a tiny little slice of the cable. Yeah, a segment of unit length, and we define its basic electrical properties. How much inductance it has per unit length, that's L0, and how much capacitance per unit length, C0.
Right, inductance and capacitance.
Using those, we can look at how voltage and current change along the line, both in space and time. And doing that leads straight to the fundamental wave equation for this system. And the math, even if we skip the step-by-step derivation, gives us some immediate big wins, right? Some key results.
Two huge ones right off the bat. First, the speed. How fast does the wave actually travel down this line?
Okay, what does the math say?
It says the velocity, v, is 1 over the square root of L0 times C0. So v equals 1 over square root of L0, C0.
Okay, dependent on inductance and capacitance per length.
But here's the really cool part. If you calculate L0 and C0 for a perfect coaxial cable, assuming, say, vacuum or air between the conductors, based purely on its geometry.
Geometry, like the radius of the inner wire and the outer shield? Exactly, just the ratio of the outer radius B to the inner radius A. When you calculate L0 and C0 based on that geometry, the product L0 times C0 turns out to be exactly 1 over C squared.
Wait, C as in the speed of light.
The speed of light in vacuum, yes.
So you're saying the speed of the wave in a perfect coax is just C, the speed of light, determined only by the physical shape.
If the space between is empty, yes. The energy travels at the speed of light. It's purely down to the geometry. It doesn't matter what the frequency is or how strong the signal is. It's locked by the shape.
That is...
Wow.
That's quite elegant. Okay, what was the second big result?
The second one is the characteristic impedance. We call it Z0. Z0.
Impedance? Okay, that sounds like resistance, VIR sort of thing.
It acts like resistance in some ways, but it's different. If you have a wave traveling purely in one direction down the line, 0 is the ratio of the voltage to the current in that wave. V over I for the traveling wave.
But there's no actual resistor component creating this ratio.
No physical resistor, no. It's defined by the line's properties. Mathematically, 0 is the square root of L0 divided by C0. Again, it comes from those per unit length values.
So it's also determined by the geometry, like the speed was.
Essentially, yes. For any given coax design, it has a specific 0 value, typically something like 50 ohms or maybe 75 ohms. You see these standard values. It behaves like a pure resistance from the wave's perspective.
And that's important for avoiding reflections, right? Matching the load.
Crucial. If you terminate the line with a load exactly equal to 0, all the energy goes into the load, no reflections. Perfect signal transfer.
Okay, so the coax cable is a pretty good solution. It guides the wave, defines the speed, defines the impedance. But you mentioned earlier, sometimes we have to ditch it. Why?
Well, coax has its limits, especially at very, very high frequencies or very high power levels.
Like what kind of limits?
Two main things. First, power handling. That central conductor and the insulation around it. If you try to pump megawatts of power through it, which you might need for, say, big radar systems or particle accelerators,
Megawatts. Okay.
yeah, that insulation can break down, arc over, it just can't handle it. Second, losses. Even in good coax, that center conductor has some resistance. At super high frequencies, skin effect makes this worse, and you lose energy as heat. It becomes inefficient.
So high power and high frequency together are tough for coax, which leads us to
The radical idea. Get rid of the center conductor entirely. Just use a hollow metal tube, a rectangular waveguide.
a hollow pipe carrying potentially megawatts of power. How does that work? Where's the energy going?
The energy is in the electromagnetic fields inside the pipe. The fields themselves fill the space. The metal walls just act as boundaries, containing the fields and guiding them along.
Okay, let's try to picture this. A rectangular metal box. See, it's got a width A and a height B.
Yeah.
What are the rules inside this box? The fields can't just do anything they want, right?
Definitely not. They have to obey Maxwell's equations, of course, but they also have to respect the boundary conditions imposed by those conducting metal walls.
And what do the walls demand?
The crucial rule is about the electric field E. It cannot have any component that runs parallel or tangential to the metal surface right at the surface. It has to hit the walls perpendicularly.
Ah, okay. So the E field lines have to go into the metal straight on, not skim along it.
Precisely. And this rule really dictates the possible shapes or modes the fields can take inside the guide. Let's think about the simplest one, the fundamental mode, often called the TE10 mode.
Okay, simplest mode. What does the electric field look like?
If you imagine looking across the width A of the guide, the electric field strength has to be 0 right at the metal walls on either side.
Because it can't be parallel to the wall.
Right, so it starts at 0, rises up to a maximum value right in the middle of the guide, and then falls back down to 0 at the other wall.
Like half a cycle of a sine wave fitting perfectly across the width A.
Exactly like that. It's a sinusoidal variation across the guide. This specific shape is forced by the boundary conditions.
And this sideways structure, this sine wave shape across A, that must affect how the wave travels down the guide along the z direction.
It absolutely does. When you take this field shape and plug it into Maxwell's equations, and you solve for how the wave propagates along the length of the guide, the z-axis, you end up with a really critical equation. It relates the wave number for propagation, Kia z, to the frequency and the guide's width.
This sounds important. What's the relationship?
The equation looks like this. KOZ squared equals omega squared over c squared minus pi squared over squared. So KOZ2 equals omega 2 C2A2.
Okay, let's unpack that. KOZ determines if the wave propagates. Omega is the angular frequency of the wave, c is the speed of light, and A is the width of the waveguide.
Correct. That equation holds the key to understanding if a wave can even travel down the guide. It connects the frequency of the signal to the physical size of the pipe.
And this leads us to something called the cutoff frequency, right?
Exactly. Look at the equation again. Kc2 equals omega 2 C2, pi 2A2. For the wave to actually propagate, to oscillate and move forward, Kz needs to be a real number. That means Kz squared must be positive.
Okay, so the first term, the frequency term, omega squared over c squared, needs to be bigger than the second term, the geometry term, pi squared over is squared.
Precisely. But what happens if the frequency omega is too low? What if that frequency term is smaller than the geometry term?
Kz squared would be negative.
Right. And if Kz squared is negative, what does that mean for Kz itself?
It has to be imaginary, the square root of a negative number.
Exactly. Kz becomes an imaginary number. And mathematically, when your wave number is imaginary, the solution to the wave equation isn't an oscillating, propagating wave anymore.
So what is it? What happens physically if Kz is imaginary?
It becomes an exponential decay. The field strength just drops off incredibly rapidly as you move down the guide from the source. It essentially dies out within a very short distance.
Doesn't travel?
Yeah.
No energy gets transmitted?
Practically none. The wave is cut off. It can't propagate. This defines the cutoff frequency, omega. It's the minimum frequency needed for that first term to be greater than or equal to the second term.
And we can calculate it.
Yes, you set the two terms equal. Omega squared c squared equals pi squared a squared. So the cutoff frequency, omega, is just pi times c divided by a, Ockel Elijah.
So the width A directly sets the minimum frequency that can pass.
That's right. The waveguide acts as a high-pass filter, purely due to its physical dimensions. If your signal frequency is below omega, determined by the width A, it just won't go through.
It's like the wave is too big or too long, low frequency, to fit properly with that bouncing pattern needed inside the guide.
That's a great way to think about it. The boundary conditions demand a certain structure, and if the wavelength is too long, it just can't establish that stable propagating pattern. It gets rejected.
Okay, fascinating.
Yeah.
But let's assume we are above the cutoff frequency. Omega is greater than omega. The wave is propagating. Now, things get weird with speed, don't they?
They get very interesting, yes. We need to talk about two different kinds of speed for the wave inside the guide. There's the phase velocity, v phase, and the group velocity, v group.
Phase velocity, that's the speed of a single point on the wave, like a crest moving.
Correct. It's the speed of a point of constant phase. Now, when you calculate this phase velocity using our propagation constant Killies, you get this result. V phase equals c divided by the square root of 1 minus omega over omega squared.
Okay, v phase, c, square root t1, HOCO 2. Now, wait a second. Since we're above cutoff, omega is greater than omega, so that fraction, HOCO, is less than 1.
Right.
Squaring it makes it still less than 1. Subtracting it from 1 gives a number between 0 and 1.
Correct.
And the square root of a number between 0 and 1 is still between 0 and 1.
Still between 0 and 1.
But the denominator in that equation, the square root term, is less than 1.
Always for a propagating wave.
Which means, if you divide c by a number less than 1, the result is greater than c. V phase is faster than the speed of light.
Mathematically, yes. The phase velocity inside the waveguide is greater than c.
Hold on. Doesn't that completely break physics? Einstein, relativity, speed limits.
But here's the crucial point. The phase velocity isn't the speed at which energy or information travels. It's the speed of an abstract mathematical point, like that crest.
Okay. How can that be?
Think about shining a laser pointer very rapidly across the face of the moon. The spot of light on the moon could, in principle, move faster than a 2 from one side to the other. But no thing, no energy, no information is actually traveling across the moon's surface at that speed. The photons are still just traveling from your laser pointer to the moon at speed c.
I see. So the phase velocity is like that spot of light. It's a pattern moving, but not the energy itself moving faster than light.
Exactly. The speed that does matter for energy transport, for sending a signal, pulse of information, that's the group velocity, v group.
Okay, so what's a group velocity doing? Is it behaving itself?
It is. The group velocity is the speed of the overall envelope or packet of the wave. And when you calculate it for the waveguide, you find this incredibly neat relationship between the two velocities.
What's the relationship?
It turns out that the phase velocity multiplied by the group velocity always equals c squared. So v phase times v group equals c squared. V phase v group equals c2.
Whoa. Okay, so v phase is greater than c.
Then for that equation to hold true, v group must be less than c.
The speed of energy, the group velocity, is always less than the speed of light. Phew. Relativity is safe.
Relativity is safe. The energy and information propagation respects the universal speed limit. It's a beautiful result, showing how interaction with the boundaries modifies the wave properties, but the fundamental laws hold.
It's amazing how that constraint just emerges from Maxwell's equations and the geometry. Okay, so we have the theory. How does this translate into practice? You hear about waveguide plumbing. It sounds quite mechanical.
It really is, because you're dealing with these precisely dimensioned hollow metal tubes, often made of copper or aluminum. You need components that fit together perfectly. Flanges, bends, twists, junctions, power dividers. It looks like high-tech plumbing.
And why go to all this trouble? Just for the high frequency and power?
Primarily, yes. Waveguides are the standard for transmitting serious RF power, especially in microwave and millimeter wave bands. Think powerful radar systems, satellite communication links, medical LINACs, scientific particle accelerators. They handle power levels that would just destroy coaxial cable.
Because there's no central conductor to melt or arc over.
Exactly. The energy is distributed in the fields within the empty space.
But how do you actually know what's going on inside? You can't just stick a multimeter probe in there.
Good question. You use specialized tools. A common technique involves cutting a very narrow slot along the length of the waveguide. You can then insert a tiny antenna, a pickup probe, through the slot and slide it along.
And what does that tell you?
Well, if you put a metal plate at the far end of the waveguide to reflect the wave back.
You create a standing wave.
Precisely. The probe moving along the slot can then measure the electric field strength. You'll find points of maximum field and points of minimum field nodes where the incoming and reflected waves interfere.
And the distance between those nodes tells you the wavelength.
Yes, it lets you measure the wavelength inside the guide, which we call the guided wavelength, lambda. And measuring that confirms the whole theory, including the relationship between frequency, cutoff, and propagation.
Clever. Now, there's one last way to think about this whole thing, right? A more intuitive picture involving reflections.
Yes, and it's a really powerful way to visualize it. Instead of thinking about this complex field pattern filling the guide, you can picture the wave inside as actually being composed of two ordinary plane waves, like waves in free space.
Two waves.
How? Imagine two plane waves crisscrossing each other, bouncing off the top and bottom walls or sidewalls of the waveguide as they travel forward. They're reflecting back and forth continuously.
Like playing billiards with light waves down a metal channel.
Kind of. The pattern we actually observe inside the guide, that standing wave across the width and propagation down the length, is simply the superposition, the combined effect of these two bouncing plane waves.
Okay, I think I can picture that. How does that help explain things like the cutoff frequency?
It makes it almost obvious. For the waves to propagate successfully, the reflections need to interfere constructively. They need to add up correctly after bouncing. This only happens if they hit the walls at the right angle.
And the angle depends on the frequency.
Exactly. If the frequency is too low, the wavelength is too long, and the waves hit the walls at too shallow an angle. The reflections end up interfering destructively. They cancel each other out. No net propagation.
But if the frequency is high enough, the angle is right for constructive interference.
Yes. The reflections reinforce each other, creating that stable propagating pattern. So this bouncing wave picture gives you a very intuitive feel for why there's a cutoff frequency. It all comes down to interference angles dictated by the guide dimensions and the wavelength.
That really ties it all together nicely. From basic transmission lines to hollow pipes, boundary conditions, weird speeds, and finally back to simple reflections.
It's a great journey through some core concepts in electromagnetism.
So let's recap the big takeaways from this deep dive. We saw how trying to send high-frequency energy down simple wires leads to radiation losses.
Which led us to guided waves, starting with the transmission line, characterized by its impedance 0 and wave velocity v, often just c.
Then we made the jump to hollow waveguides, where the metal boundaries dictate the field patterns and lead to the crucial concept of the cutoff frequency, omega.
Making waveguides act like high-pass filters, only frequencies above cutoff can propagate.
And finally, we wrestled with the speed paradox. Phase velocity faster than light, but group velocity, the energy speed, always less than light, neatly related by v phase times v group equals c squared.
A fantastic illustration of relativistic principles emerging from classical E&M.
What really stands out, I think, is that relationship. V phase v group equals c2. It's such a stark reminder that our intuitive ideas about speed can be subtle in physics. A wave crest can break the light barrier mathematically, but the universe's actual speed limit on energy and information remains absolute, enforced by the very geometry guiding the wave.
It really connects the dots between geometry, field theory, and relativity in a very concrete way.